Welcome back to Velarin Sleepy Space Mysteries. Tonight we begin a very old story. Not the story of a single star, not even the story of a galaxy, but the story of everything, the story of the universe itself. Perhaps you've had a long day, or perhaps you simply enjoy drifting into sleep while your thoughts wander among distant stars. Either way, you don't need to do anything right now except relax. Let your breathing slow. Let the noise of the day soften and fade. And as your mind grows quieter, imagine traveling backward through time, past the turning of galaxies, past the birth of stars, past the formation of the very atoms that make up your body. Earlier and earlier we go, toward a moment when the entire universe was smaller than a grain of sand. Long before planets, long before light could move freely through space. Just a beginning. If you enjoy these quiet journeys through the mysteries of space, you might also enjoy another Velarin episode where we explore what happens near the edge of a black hole, where time itself begins to behave strangely. But tonight, our path goes in the opposite direction, toward the first moment of cosmic history. Before we continue, consider gently tapping the like button, subscribing, and ringing the bell so more curious minds can find their way to these peaceful explorations. And I'd love to know something simple before we begin. Where in the world are you listening from tonight? Somewhere beneath quiet city lights? A countryside filled with stars? Or perhaps a dark room where only your imagination is awake? Wherever you are, settle in. Because the story of the universe begins in a place where time itself was only just beginning to exist. And the first chapter of that story is almost impossibly small. The story of the universe begins in a place where our understanding becomes quiet and uncertain. If we travel backward through cosmic history, past the formation of galaxies, past the first stars, past even the earliest atoms, we eventually reach a moment where the familiar rules of nature begin to blur. Temperatures rise beyond anything we can easily imagine. Space itself shrinks smaller and smaller. Time ticks faster and faster toward a limit that seems almost impossible to approach. This earliest moment that physics can meaningfully describe is known as the Planck epoch. It lasted for only the tiniest fraction of a second after the universe began expanding. To understand just how brief this moment was, imagine the entire 13.8 billion year history of the cosmos compressed into a single calendar year. Within that immense timeline, the Planck epoch would occupy a span smaller than the blink of an eye, smaller even than the tiniest flicker of thought before sleep. And yet within that unimaginably brief instant, the foundations of everything that would ever exist were already beginning to take shape. During the Planck epoch, the universe was extraordinarily small, far smaller than a single atom. It was also unimaginably hot, with temperatures reaching levels that modern physics can barely describe. At these extremes, the familiar ingredients of nature behaved very differently. The four fundamental forces that govern the universe today had not yet separated into the distinct forces we recognize. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were likely blended together into a single unified interaction. Instead of four different forces shaping reality, there may have been only one. In this early state, space and time themselves were not smooth and calm the way they appear on large cosmic scales today. Instead, they may have behaved more like a restless sea of energy, constantly fluctuating and shifting. Physicists sometimes describe this condition as quantum foam. Tiny ripples in spacetime would appear and vanish almost instantly, like bubbles forming and popping on the surface of boiling water. But here is where our knowledge reaches a frontier. The mathematics of Einstein's theory of gravity works beautifully when describing planets, stars, and galaxies. Quantum mechanics works equally well when describing atoms and subatomic particles. Yet, at the extreme conditions of the Planck epoch, these two powerful theories collide. Gravity becomes so strong and quantum effects become so intense that neither theory alone can fully describe what is happening. Somewhere in that earliest instant lies a deeper theory that physicists are still searching for, a theory often called quantum gravity, which would unite the large-scale structure of spacetime with the microscopic behavior of particles. Until such a theory is fully understood, the Planck epoch remains a kind of horizon in our knowledge. We can approach it with equations and careful reasoning, but beyond it the details remain hidden. Still, even though we cannot see past that boundary, we can describe what likely happened next. As the universe expanded, it began to cool ever so slightly. That cooling allowed the first important transformation to occur. The unified force that governed the earliest universe began to separate. Gravity, the force that shapes galaxies and bends the paths of light, may have been the first to split away from the others. Imagine a perfectly symmetrical crystal that suddenly begins to form subtle patterns as it cools. What was once uniform becomes structured. This process is known as symmetry breaking, and it played a crucial role in shaping the laws of physics that govern our universe today. Once gravity separated, the remaining forces continued to evolve as the universe expanded and cooled further. Eventually, the strong nuclear force would become distinct, followed later by the separation of the electromagnetic force and the weak nuclear force. Each of these transitions quietly rewrote the rules of the cosmos. The forces that bind atomic nuclei together, the forces that allow stars to shine, and the forces that govern radioactive decay were all emerging from these early transformations. It is remarkable to realize that the behavior of atoms in your body today can be traced back to these delicate shifts that occurred in the first fractions of a second after the universe began. But the universe was not finished changing. Something even more dramatic was about to happen. In the next brief instant of cosmic history, space itself would expand at an astonishing rate, growing faster than light could travel across it. A tiny region of the newborn universe would suddenly balloon outward, stretching spacetime on a scale that is almost impossible to visualize. This extraordinary event is known as cosmic inflation, and it would shape the structure of the universe in ways that are still visible across the sky today. As the newborn universe continued to expand and cool from the unimaginable conditions of the Planck epoch, it approached a moment that would permanently shape the large-scale structure of everything we see today. The universe was still incredibly small, far smaller than a single atom, yet within a tiny fraction of a second something extraordinary occurred. Instead of expanding gradually, the universe suddenly experienced a brief but explosive growth spurt known as cosmic inflation. To picture this, imagine a balloon that begins as a tiny speck and then suddenly swells to enormous size almost instantly. But even that comparison is too gentle. Inflation was not simply fast expansion. It was expansion so extreme that distances between points in space grew faster than light itself could travel across them. This might sound like a violation of the cosmic speed limit set by relativity, but it is not. Nothing was moving through space faster than light. Instead, space itself was stretching, carrying everything within it along for the ride. The entire event lasted for only a fleeting moment, perhaps less than a trillionth of a second. Yet, during that tiny interval, the universe expanded by an almost unimaginable factor. A region smaller than a proton could have grown large enough to contain the entire observable universe we see today, including billions of galaxies spread across vast cosmic distances. Why this sudden expansion occurred remains one of the most fascinating puzzles in modern cosmology. One of the leading ideas involves a special form of energy associated with a field known as the inflaton field. Fields are not unfamiliar in physics. The electromagnetic field surrounds charged particles and allows forces to act across space. In a similar way, the inflaton field may have filled the early universe with an immense amount of stored energy. For a brief time, this energy dominated everything else in existence. Instead of behaving like ordinary matter or radiation, it exerted a kind of pressure that caused space to expand at an accelerating rate. The more space expanded, the more room there was for the field's energy to drive further expansion, creating a rapid runaway growth of spacetime itself. This expansion had an important side effect. In the earliest moments before inflation, the universe may have been uneven and chaotic, filled with tiny irregularities. But inflation stretched space so dramatically that any large variations were smoothed out, much like wrinkles disappearing when fabric is pulled tightly. This helps explain something scientists have observed when they study the universe on the largest scales. No matter which direction astronomers look into the distant cosmos, the universe appears remarkably uniform. Galaxies are scattered throughout space in patterns that, on average, look very similar everywhere. The temperature of ancient radiation filling the universe is nearly identical in every direction. Without inflation, it would be difficult to explain how regions so far apart could end up looking so alike. Inflation also amplified something extremely subtle: tiny quantum fluctuations that existed in the early universe. Even in empty space, quantum physics tells us that small energy variations constantly appear and disappear. Normally, these fluctuations are microscopic and vanish almost instantly. But during inflation, the rapid stretching of space magnified these tiny irregularities into slightly denser and slightly thinner regions of matter and energy. These small differences would become incredibly important later. Billions of years afterward, gravity would pull more matter into the slightly denser regions, gradually forming the first galaxies and clusters of galaxies. In other words, the enormous cosmic structures we see today may ultimately trace their origins back to tiny quantum ripples that were stretched across the universe during this brief inflationary burst. Eventually, inflation came to an end. The energy stored in the inflaton field did not disappear quietly. Instead, it transformed into a tremendous outpouring of particles and radiation. Physicists sometimes describe this transition as reheating, because the universe, which had cooled slightly during inflation's rapid expansion, suddenly filled again with intense heat and energy. The cosmos was now a blazing sea of particles moving at incredible speeds. Space had grown enormously larger than it had been before inflation began, yet the universe remained extremely dense and hot. This moment marked the true beginning of what scientists usually refer to as the hot Big Bang phase of cosmic history. Within this fiery environment, the raw energy of the universe began to transform into the first fundamental particles. Quarks, electrons, neutrinos, and other building blocks of matter emerged from the energetic radiation filling space. They collided, scattered, and transformed in a chaotic dance governed by the laws of particle physics. And hidden within that violent early environment was a delicate imbalance that would determine whether the universe would contain anything at all. Because for every particle of matter that formed, an equal partner known as antimatter was also created. And when matter and antimatter meet, they destroy one another in flashes of pure energy. If perfect symmetry had prevailed in those early moments, every particle would have annihilated with its opposite, leaving behind nothing but radiation. No atoms, no stars, no galaxies, no life. Yet somehow the universe avoided that fate. Somewhere within the first seconds of cosmic history, a tiny advantage emerged. Matter would survive, just barely. As the universe settled into the hot, dense state that followed cosmic inflation, it became a vast ocean of energy and rapidly forming particles. Temperatures were still extraordinarily high, far beyond anything that exists naturally in the universe today. In this intense environment, energy constantly transformed into particles, and particles into energy again, following one of the most fundamental principles in physics. Energy and matter are interchangeable. From this churning sea of energy, the first building blocks of matter began to appear. Tiny particles called quarks emerged alongside electrons, neutrinos, and a variety of other short-lived particles. Quarks quickly combined in groups of 3 to form slightly larger particles known as protons and neutrons, which would later become the cores of atoms. But there was an important twist to this process. Every time a particle formed, its mirror opposite appeared as well. For every electron there was a positron, its antimatter twin carrying the same mass but opposite electric charge. For every proton there was an antiproton, identical in mass but opposite in certain quantum properties. These pairs were created constantly in the energetic environment of the early universe. And whenever a particle met its antimatter counterpart, something dramatic happened. They annihilated each other instantly. Their mass vanished in a burst of pure radiation, releasing energy that raced away as high-energy photons. In those first moments of cosmic history, this cycle happened endlessly. Particles appeared, collided, vanished, and reappeared again in an ongoing exchange between matter and energy. If this balance had remained perfect, the universe would have evolved into something very different from what we see today. In a perfectly symmetrical universe, matter and antimatter would have been created in exactly equal numbers. As the universe cooled, nearly every particle would eventually have met its opposite. Each pair would have annihilated, leaving behind only radiation. The cosmos would contain no atoms, no stars, no galaxies. It would be filled with nothing but a thin bath of energy drifting through expanding space. But that is not the universe we inhabit. Instead, something subtle happened during those early seconds. For reasons that are still not completely understood, the laws of physics appear to have allowed matter to gain the slightest advantage over antimatter. The difference was incredibly small. Out of roughly 1 billion pairs of matter and antimatter particles, there may have been one extra particle of matter. Just one. At first glance, this tiny imbalance seems insignificant, almost too small to matter at all. Yet, as the universe continued cooling, annihilations between particles and antiparticles began to dominate. Pairs met and vanished in flashes of energy across the cosmos. Billions upon billions of them disappeared. But those few extra particles of matter had no partners to destroy them. After the great wave of annihilation subsided, the universe was left with a faint residue of matter. That leftover fraction, perhaps only one particle for every billion original pairs, survived the fiery chaos of the early universe. And from that small remainder, everything else eventually formed. Every atom in every galaxy, every star that has ever shone, every planet that has ever existed, and every living being that has ever looked up at the night sky is built from that tiny imbalance. This puzzle is known as baryon asymmetry, and it remains one of the deepest mysteries in cosmology and particle physics. Scientists have spent decades trying to understand why matter won this cosmic contest by such a narrow margin. One possibility involves subtle violations in the symmetry of physical laws. In many situations, the equations of physics treat matter and antimatter as perfectly interchangeable. But experiments have shown that certain rare particle interactions behave slightly differently depending on whether matter or antimatter is involved. These effects are called CP violations, short for charge parity violations. Although these asymmetries have been observed in laboratories, the amount discovered so far is not quite large enough to fully explain the imbalance seen across the entire universe. Another idea suggests that exotic particles may have existed in the earliest moments after the Big Bang. These hypothetical particles could have decayed in ways that favored matter over antimatter, leaving behind the small excess that survived annihilation. If such particles existed, they would have disappeared almost instantly, leaving only indirect traces in the structure of the universe we observe today. Whatever the explanation turns out to be, the result was profound. The universe that emerged from those early seconds was no longer perfectly symmetrical. Instead, it contained a small but crucial amount of matter that would later gather together under the influence of gravity. Yet, at this stage, the universe was still far too hot for atoms to exist. Protons and neutrons raced through space at enormous speeds, colliding with one another in a dense plasma of particles and radiation. Electrons were present as well, but they could not yet attach themselves to atomic nuclei. Everything was still too energetic. However, as the universe continued expanding, the temperature slowly began to fall. And within just a few minutes after the beginning of cosmic expansion, something remarkable happened. The first atomic nuclei in the universe began to form. As the universe continued expanding, something gentle but important was happening at the same time. The temperature of the cosmos was slowly falling. In the earliest seconds after expansion began, the universe was far too hot for particles to remain bound together. Collisions were violent and constant. Any small structure that attempted to form would immediately be broken apart by energetic radiation. But expansion changed that environment. As space stretched outward, energy became diluted across larger distances. With less energy packed into every region of space, the temperature gradually dropped. It was still unimaginably hot by everyday standards, but compared to the earlier moments of cosmic history, the universe was beginning to calm. About 1 second after the beginning of expansion, the universe had cooled enough for protons and neutrons to exist relatively stably. These particles were still racing through space at incredible speeds, surrounded by electrons, neutrinos, and an intense bath of radiation. Yet the basic building blocks of atomic nuclei were finally present. Neutrons, however, had a slight disadvantage. Unlike protons, which can remain stable indefinitely, free neutrons tend to decay over time. If left alone long enough, a neutron transforms into a proton, releasing an electron and a neutrino in the process. In the early universe, this meant that neutrons were slowly disappearing unless they could quickly find partners and bind together inside atomic nuclei. This race against time set the stage for one of the most important episodes in cosmic history: primordial nucleosynthesis. Only a few minutes after the universe began expanding, temperatures dropped just enough for protons and neutrons to start combining. When these particles collided at the right energies, they could bind together through the strong nuclear force, forming the nuclei of the simplest elements. The first stable nucleus to form was deuterium, a type of hydrogen nucleus containing 1 proton and 1 neutron. Once deuterium existed, it could combine with additional protons and neutrons to form slightly heavier nuclei such as helium-3 and helium-4. These reactions spread rapidly across the universe. Within just a few minutes, enormous numbers of helium nuclei were created as protons and neutrons fused together in the hot cosmic plasma. But the process did not continue indefinitely. The universe was expanding quickly, and the falling temperature soon made it difficult for nuclear reactions to continue. Once the cosmic temperature dropped below a certain threshold, collisions no longer had enough energy to overcome the electrical repulsion between positively charged nuclei. As a result, primordial nucleosynthesis lasted only a brief window of time, perhaps around 20 minutes in total. Yet, in that short span, the chemical foundation of the entire universe was established. When the process ended, the universe contained a very specific mixture of elements. Roughly 75% hydrogen nuclei and 25% helium nuclei by mass, with tiny traces of a few slightly heavier isotopes such as lithium. No heavier elements existed yet. Carbon, oxygen, iron, and all the other elements that make up planets, oceans, mountains, and living organisms had not been created. Those would come much later, forged inside the cores of stars and scattered across space by exploding supernovae. For now, the universe was a vast glowing ocean composed almost entirely of hydrogen and helium nuclei. Electrons were still moving freely through this plasma, unable to settle into stable orbits around nuclei because the temperature remained far too high. Photons, the particles of light, constantly scattered off these charged particles, bouncing endlessly in all directions. This meant that the universe was still opaque. Even though it was filled with intense radiation, light could not travel far without colliding with something. Photons were trapped inside the plasma, much like sunlight trapped inside the dense interior of a star. If an observer could somehow exist during this period, they would not see distant objects or stars. The entire universe would appear as a brilliant, glowing fog of energy and particles. But slowly, patiently, expansion continued its quiet work. As hundreds of thousands of years passed, the temperature of the universe continued to fall. The violent collisions between particles became less frequent. The dense plasma gradually calmed, approaching a threshold where something entirely new could finally occur. For the first time in cosmic history, electrons would be able to settle into stable orbits around atomic nuclei. Atoms would finally form, and when that happened, light itself would be set free. For hundreds of thousands of years after the first atomic nuclei formed, the universe remained in a strange and glowing state. It was filled with hydrogen and helium nuclei, countless free electrons, and an immense sea of photons moving rapidly in every direction. Temperatures were still extremely high, though far cooler than the fiery conditions of the universe's earliest minutes. Space continued expanding, and with every passing moment the density and temperature of the cosmos slowly declined. Yet light was still trapped. Photons constantly collided with free electrons, scattering again and again through the dense plasma that filled the universe. Every time a photon tried to travel forward, it struck another charged particle and bounced away in a different direction. This endless scattering meant that light could not move freely across space. Instead, radiation and matter were tightly coupled together, behaving almost like a thick, luminous fog stretching across the entire cosmos. Imagine standing inside an enormous cloud so dense that you cannot see even a few steps ahead. Light exists everywhere around you, yet nothing is visible because photons cannot travel very far before being scattered. In a similar way, the young universe was filled with light but remained effectively opaque. During this long period, the cosmos had no stars, no galaxies, and no planets. The universe was still far too uniform for such structures to form. Matter was distributed almost evenly across space, with only the faintest hints of variation. These tiny differences in density had been seeded earlier during cosmic inflation, but for now they remained subtle ripples hidden inside the glowing plasma. Time continued to pass. As the universe expanded, temperatures gradually dropped to a critical threshold. After roughly 380,000 years, conditions finally became cool enough for something profoundly important to occur. Electrons, which had been racing freely through space since the beginning, were now able to slow down enough to become captured by atomic nuclei. For the first time, stable neutral atoms formed. Hydrogen atoms appeared as electrons settled into orbit around single protons. Helium atoms formed as electrons bound to helium nuclei. This transformation might sound simple, but its consequences were enormous. Once electrons became bound inside atoms, they could no longer scatter photons nearly as efficiently as free charged particles had done. Suddenly, the fog that filled the universe began to clear. Photons that had been trapped for hundreds of thousands of years could finally travel long distances without constant collisions. Light was set free. This moment in cosmic history is known as recombination, even though it was technically the first time electrons and nuclei had combined in the first place. The name reflects the idea that charged particles were coming together to form neutral atoms. As recombination spread across the universe, photons streamed outward in every direction, racing through space without obstruction. Those ancient photons have been traveling ever since, crossing billions of light years and continuing their journey even today. They still fill the universe, but over billions of years, the expansion of space has stretched their wavelengths dramatically. What once began as extremely energetic radiation has gradually cooled and shifted into the microwave portion of the electromagnetic spectrum. Today, this faint relic radiation is known as the cosmic microwave background, often abbreviated as the CMB. It is the oldest light that astronomers can observe. No matter where scientists point their instruments in the sky, they detect this soft microwave glow. It arrives from every direction almost perfectly evenly, a quiet echo of the moment when the universe first became transparent. In many ways, the cosmic microwave background acts like a photograph of the universe when it was only 380,000 years old. Long before stars ignited or galaxies assembled, this ancient light captured the subtle patterns of matter that existed at that time. And hidden within those patterns are delicate variations in temperature, differences so small that they amount to only a few millionths of a degree. Yet those tiny variations would eventually grow into something remarkable. Over immense stretches of time, gravity would slowly pull matter toward the slightly denser regions recorded in that ancient light. Gas would gather into clouds. Clouds would collapse into the first stars. Stars would cluster into galaxies, and galaxies would weave themselves into the vast cosmic web that fills the universe today. The structures we see across the night sky began as faint ripples imprinted on the universe when it was still an infant. But after recombination, the universe entered a long and quiet era. The first light had been released, yet no new stars had appeared to replace it. The cosmos had become transparent, but it was also about to become dark. This next chapter of the story is known as the Cosmic Dark Ages, a time when the universe waited patiently for the first stars to ignite. When the universe finally became transparent about 380,000 years after the beginning of cosmic expansion, something remarkable happened that still affects every corner of space today. Light that had been trapped for hundreds of thousands of years suddenly began traveling freely across the universe. Those ancient photons streamed outward in all directions, filling the expanding cosmos with a faint but persistent glow. Even now, billions of years later, that same light continues to move quietly through space. This ancient radiation is known as the cosmic microwave background, often shortened to CMB. It is the oldest light that scientists can observe, a delicate afterglow left behind from the early universe when atoms first formed and photons were finally able to travel unimpeded. If human eyes could detect microwave radiation, the sky would never appear truly dark. Instead, we would see a soft glow coming from every direction at once, a dim but uniform light that surrounds us completely. The cosmic microwave background fills the entire universe like a quiet echo of the moment when matter and radiation first went their separate ways. Over the immense span of cosmic history, the expansion of space has stretched these ancient photons dramatically. When they were first released, their energy corresponded to temperatures of several thousand degrees. But as space expanded, the wavelengths of the photons lengthened, cooling their energy more and more. Today, the cosmic microwave background corresponds to a temperature of just a few degrees above absolute zero. Despite its faintness, the CMB carries an extraordinary amount of information about the early universe. It acts like a snapshot taken at the moment when the cosmic fog lifted. At that time, the universe was still very young, smooth, and simple compared to the complex structure we see today. Galaxies had not yet formed. Stars had not yet ignited. Yet the seeds of all those future structures were already present, hidden within subtle variations in the distribution of matter. For a long time, however, scientists did not even know this ancient radiation existed. Its discovery came almost by accident in the mid-20th century. Two radio engineers working with a sensitive antenna were attempting to measure faint signals from space. No matter how carefully they adjusted their equipment, they kept detecting a persistent background noise. The signal seemed to come from everywhere in the sky equally. It did not disappear when they pointed their antenna in different directions. At first, they suspected something was wrong with the instrument. They checked every component, cleaned the antenna, and even removed nesting birds that had taken shelter inside it. Yet the mysterious signal remained. What they had unknowingly discovered was the faint microwave glow of the early universe. At almost the same time, theoretical physicists had been predicting that such radiation should exist if the universe had once been extremely hot and dense. When the observational discovery was compared with the theoretical predictions, the conclusion became clear. The faint hiss detected by the antenna was the leftover radiation from the moment when the universe first became transparent. The discovery of the cosmic microwave background provided powerful evidence that the universe had indeed begun in a hot, dense state. It transformed cosmology from a largely theoretical field into one supported by direct observational proof. At first glance, the cosmic microwave background appears almost perfectly uniform. Measurements show that its temperature is nearly identical in every direction of the sky. This remarkable smoothness tells us that the early universe was extremely even in its distribution of matter and energy. But when instruments became more sensitive, scientists noticed something extraordinary hidden within that smooth glow. Tiny fluctuations. The temperature of the CMB is not perfectly identical everywhere. In some places it is slightly warmer, in others slightly cooler. The differences are incredibly small, only about 1 part in 100,000. Yet these tiny variations represent regions where matter in the early universe was slightly denser or slightly thinner. Those subtle variations would eventually shape the entire structure of the cosmos. Over billions of years, gravity would amplify the denser regions, slowly pulling matter together into enormous clouds of gas. Those clouds would collapse to form the first stars. Clusters of stars would gather into galaxies, and galaxies would arrange themselves into the vast cosmic web that stretches across the universe today. In other words, the galaxies scattered across the night sky may trace their origins back to tiny ripples imprinted in the universe when it was only a few 100,000 years old. But after this ancient light began its long journey through space, the universe entered a period that was strangely quiet. Atoms existed now. Photons moved freely across the cosmos. Yet no stars had formed, and no galaxies shone. The universe had become transparent, but it had also grown profoundly dark. A long era of cosmic night was about to begin. This chapter of cosmic history is known as the Cosmic Dark Ages, a time when gravity slowly prepared the stage for the first stars that would eventually bring light back to the universe. After the release of the cosmic microwave background, the universe entered a long and quiet chapter of its history. Light from the early universe continued traveling freely across space, but new sources of light had not yet appeared. The first stars had not formed. Galaxies did not yet exist. The cosmos was filled mostly with neutral hydrogen and helium drifting through an ever-expanding sea of space. This period is often called the Cosmic Dark Ages. If an observer could have existed somewhere in the universe during this time, the sky would have been profoundly dark. The faint glow of the cosmic microwave background would still exist, but it would not appear as visible light. There would be no stars to illuminate the darkness, no galaxies stretching across the sky, no familiar constellations. Space would feel vast, silent, and almost empty. Yet beneath this quiet darkness, something important was slowly unfolding. The universe was not perfectly uniform. Earlier, we encountered the tiny temperature variations imprinted within the cosmic microwave background. These subtle fluctuations corresponded to regions where matter was slightly more concentrated or slightly less dense than average. At the time, they seemed almost insignificant differences measured in fractions of a degree. But gravity is patient. Even the smallest imbalance can grow over immense stretches of time. Regions containing slightly more matter exerted slightly stronger gravitational pull. Nearby gas was gently drawn toward these denser areas. As more matter gathered, gravity strengthened further, attracting even more material. Over millions of years, these small differences began to grow. Clouds of hydrogen and helium slowly collected within invisible wells of gravity. These wells were not formed only by ordinary matter. Much of the gravitational structure guiding the universe was created by something far more mysterious: dark matter. Dark matter does not emit light, absorb light, or interact with radiation in the way ordinary matter does. Yet it possesses mass, and that mass exerts gravitational influence. Astronomers believe dark matter makes up far more of the universe's total matter than the atoms we can see. In the early universe, dark matter began clumping together first. Its gravitational pull created large-scale scaffolding across space. Ordinary gas then flowed into these dark matter structures, gradually forming enormous clouds. These growing regions became the first gravitational seeds of future galaxies. At first, the process was incredibly slow. Gas drifting through space took millions of years to gather into large clouds. The universe was expanding at the same time, which made it even harder for gravity to overcome the outward stretching of space. But eventually, certain regions accumulated enough mass that gravity began to dominate. Gas clouds grew denser and denser. As matter collapsed inward, temperatures inside the clouds began to rise. The compression of gas caused particles to collide more frequently, heating the cloud's interior. Deep within these growing structures, conditions were gradually approaching something familiar: the birth of stars. However, the first stars were not like the ones we see in the night sky today. The early universe contained almost no heavy elements. It was composed almost entirely of hydrogen and helium left over from primordial nucleosynthesis. Without heavier elements to help cool collapsing gas clouds efficiently, the first stars grew far larger than typical modern stars. Many scientists believe the earliest stars were enormous. Some may have contained hundreds of times the mass of our Sun. These giant stars burned extremely hot and bright, but they also lived very short lives. Their immense mass caused nuclear fusion to proceed rapidly, exhausting their fuel much faster than smaller stars. Yet before these stars could ignite, something important had to occur. The collapsing clouds of gas needed to reach a critical point where pressure and temperature in the center became high enough for nuclear fusion to begin. Fusion is the process that powers stars. It occurs when hydrogen nuclei collide with enough energy to merge together, forming helium and releasing tremendous amounts of energy in the process. Once fusion begins, a star is born. And when the first stars finally ignited, they brought light back to the universe for the first time since the cosmic microwave background had faded. These early stars marked the end of the cosmic dark ages. But their influence extended far beyond simple illumination. The intense ultraviolet radiation produced by these massive stars began transforming the surrounding hydrogen gas. Neutral atoms were stripped of their electrons once again, turning the calm cosmic fog into ionized plasma. This transformation would gradually reshape the entire universe. The era that followed is known as cosmic reionization, when the light from the first stars began to sweep across the cosmos and lift the long night that had lasted for hundreds of millions of years. And as the first stars lived and died, they would begin forging the heavier elements that would eventually make planets, oceans, and life possible. The universe was slowly awakening. For hundreds of millions of years after the universe became transparent, the cosmos remained quiet and dark. Vast clouds of hydrogen and helium drifted through space, slowly gathering under the influence of gravity. The tiny fluctuations seeded in the earliest moments of cosmic history continued growing, pulling more matter into their invisible gravitational wells. Although nothing yet shone in the darkness, the universe was patiently preparing for a dramatic transformation. Eventually, In some of the densest regions of these growing clouds, gravity pushed matter inward with increasing strength. Gas compressed toward the center of each cloud, and as it did, the temperature deep inside began to rise. At first, the heating was slow, but as more material collapsed inward, the process accelerated. Particles collided more frequently, and the pressure at the center climbed higher and higher. Finally, a threshold was crossed. When temperatures reached millions of degrees, hydrogen nuclei began colliding with enough energy to overcome their natural electrical repulsion. Instead of bouncing apart, some of them fused together, forming helium. In that moment, nuclear fusion ignited. The first stars were born. These earliest stars are known as population 3 stars, the very first generation of stars in the universe. They were fundamentally different from the stars we see today. Because the early universe contained almost no heavy elements, the gas clouds that formed them cooled less efficiently. Without strong cooling, collapsing clouds tended to form extremely massive stars rather than many smaller ones. As a result, the first stars were likely enormous. Some may have reached masses hundreds of times greater than our Sun. Their immense size made them extraordinarily bright, pouring vast amounts of ultraviolet radiation into the surrounding darkness. Yet this brilliance came at a cost. Massive stars burned their nuclear fuel at a furious rate, and the first stars lived very short lives compared to the billions of years enjoyed by smaller stars like our Sun. Many of them may have existed for only a few million years, but during that brief time, they transformed the universe. The intense radiation pouring from these stars began interacting with the hydrogen gas that filled space. Earlier in cosmic history, during recombination, hydrogen atoms had captured electrons and become neutral. Now the energetic ultraviolet light from the first stars reversed that process. Photons struck hydrogen atoms and knocked their electrons free again, turning neutral gas back into ionized plasma. This process is known as reionization. At first, reionization occurred only in small regions around individual stars and early star clusters. Each star carved out a glowing bubble of ionized gas within the surrounding darkness. As more stars formed within early galaxies, these bubbles expanded and began to overlap. Gradually, over hundreds of millions of years, the ionized regions spread farther and farther across space. The universe slowly became transparent once again to energetic radiation. The dense fog of neutral hydrogen that had dominated the cosmic dark ages began to fade. Light from young galaxies could now travel much greater distances through the universe. In this way, the first stars ended the cosmic dark ages and ushered in a new era of cosmic illumination. But the influence of these stars extended far beyond simply lighting the universe. Inside their cores, nuclear fusion began forging elements that had never existed before. While primordial nucleosynthesis had produced mostly hydrogen and helium, stellar fusion allowed heavier elements to form. Carbon, oxygen, neon, and other elements began emerging inside the blazing hearts of these early stars. When the most massive of these stars reached the end of their short lives, they did not fade quietly. Instead, many of them exploded as powerful supernovae, scattering newly created elements across the surrounding universe. These explosions enriched nearby gas clouds with heavier atoms for the first time. The next generation of stars would form from this enriched material. With the presence of heavier elements, gas clouds could cool more efficiently during gravitational collapse. This allowed future stars to form in a wider variety of sizes, including smaller and longer-lived stars like the ones that populate galaxies today. In this way, the deaths of the first stars prepared the universe for a far more complex cosmic future. Over time, groups of stars began clustering together within growing clouds of matter, forming the earliest proto-galaxies. These primitive galaxies were smaller and more chaotic than the large spiral and elliptical galaxies we observe today, but they marked the beginning of the grand cosmic structures that would eventually fill the universe. Gravity continued weaving these structures together, forming vast filaments and clusters across space. The cosmic web was beginning to take shape. Yet even as galaxies slowly assembled, another mystery was quietly revealing itself in the background of cosmic history. The universe was still expanding, just as it had been since the very beginning. For billions of years, scientists assumed that gravity would eventually slow that expansion down. But much later, when astronomers began measuring the motion of distant galaxies with greater precision, they would discover something astonishing. The universe was not slowing its expansion, it was accelerating. And that discovery would introduce one of the most mysterious forces in all of cosmology. After the first stars ignited and began illuminating the universe, cosmic history entered a new and increasingly dynamic phase. The darkness that had once dominated the cosmos slowly retreated as more stars formed within growing regions of matter. These stars did not exist in isolation. They were gathering together in clusters, bound by gravity inside structures that would gradually evolve into the first galaxies. At the beginning, these early galaxies were quite different from the majestic spirals and giant ellipticals we see in the universe today. They were smaller, irregular, and chaotic. Gas flowed into them from surrounding space, feeding new bursts of star formation. Powerful radiation from young stars illuminated their surroundings, while violent supernova explosions stirred the gas and scattered newly created elements outward. Each generation of stars changed the universe slightly. The earliest stars had formed from nearly pure hydrogen and helium. But once the first supernova explosions enriched space with heavier elements, future stars could form under different conditions. These heavier elements allowed gas clouds to cool more efficiently as they collapsed. This cooling made it easier for clouds to fragment into smaller pieces, leading to the formation of stars with a wider range of masses. Over time, stars began forming in enormous numbers. Inside growing galaxies, swirling clouds of gas collapsed again and again, producing stellar nurseries where thousands of new stars ignited. Many of these stars gathered into dense star clusters, while others spread throughout the forming galaxies, tracing the shapes of spiral arms or filling elliptical halos of light. Meanwhile, gravity was not only shaping individual galaxies, it was also weaving together something far larger. Earlier, we encountered the mysterious substance known as dark matter, which does not emit light but exerts powerful gravitational influence. In the early universe, Dark matter had begun clumping together long before ordinary matter gathered into stars. These invisible structures formed a vast cosmic framework across space. As ordinary matter fell into the gravitational wells created by dark matter, galaxies began forming along enormous filaments stretching across the universe. These filaments connected massive clusters of galaxies while leaving vast empty regions between them. The result is what scientists now call the cosmic web. If we could somehow step far outside our galaxy and look at the universe on its largest scales, we would not see galaxies scattered randomly in all directions. Instead, we would see a breathtaking network of glowing threads stretching across immense distances. Galaxies gather along these filaments like dew droplets along strands of a spider's web. Between the filaments lie enormous cosmic voids, regions containing very few galaxies at all. Some of these voids span hundreds of millions of light years, vast bubbles of space where matter is comparatively scarce. The structure of the cosmic web developed gradually over billions of years as gravity continued amplifying the tiny density variations that had existed since the early universe. Regions with slightly more matter attracted even more material, growing into massive galaxy clusters. Less dense regions lost matter and became the enormous voids that stretch between the filaments. Within the densest clusters, galaxies often interacted with one another in dramatic ways. Gravity pulled them together, causing galaxies to pass close by each other or even collide and merge. When galaxies merge, their stars usually pass by one another without direct collision because the distances between stars are so vast. But the gas clouds inside the galaxies can crash together, triggering enormous bursts of star formation. Over time, many small galaxies merged into larger ones. This process helped shape the enormous galaxies we see today. Our own Milky Way likely formed through a long history of mergers with smaller galaxies, gradually building up its spiral structure and stellar population over billions of years. As galaxies continued evolving, they also began forming new kinds of cosmic objects. Some of the earliest massive stars collapsed into black holes at the ends of their lives. In the dense centers of galaxies, these black holes could grow by consuming gas and merging with other black holes. Eventually, many galaxies developed supermassive black holes at their centers, containing millions or even billions of times the mass of the Sun. These enormous objects influence the structure and evolution of their host galaxies in ways astronomers are still trying to fully understand. By the time the universe reached an age of roughly 1 billion years, galaxies had become common across space. Stars shone throughout the cosmos, lighting the vast cosmic web with countless points of brilliance. The long darkness that had once dominated the universe had given way to a rich and evolving cosmic landscape. Yet even as galaxies flourished and stars filled the sky, the universe itself continued expanding. For billions of years, scientists assumed that gravity from all this matter would gradually slow that expansion. After all, gravity pulls things together. It seemed natural that the growth of the universe would eventually decelerate under the combined gravitational pull of galaxies and dark matter. But when astronomers finally measured the expansion carefully enough, they discovered something unexpected. The expansion of the universe was not slowing down. It was speeding up. and that realization would introduce one of the greatest mysteries in modern cosmology. By the time the universe had aged several billion years, it had become a richly structured cosmos filled with galaxies, stars, and enormous clusters of matter stretching across the cosmic web. The once simple universe of hydrogen gas and faint radiation had transformed into something far more complex. Spiral galaxies rotated gracefully through space. Elliptical galaxies glowed with billions of aging stars, and massive galaxy clusters gathered along vast filaments of dark matter. Through all of this time, one fundamental behavior of the universe had continued without interruption. Space itself kept expanding. Ever since astronomers first discovered that distant galaxies are moving away from us, scientists understood that the universe was growing larger. When light travels through expanding space, its wavelength stretches along with that expansion. This stretching shifts the light toward the red end of the spectrum, a phenomenon known as cosmic redshift. By measuring how much a galaxy's light has been redshifted, astronomers can determine how fast it is moving away. The farther away a galaxy lies, the faster it appears to recede. This pattern reveals the steady expansion of space itself. For most of the 20th century, scientists assumed that gravity would gradually slow this expansion. After all, the universe contains enormous amounts of matter. Galaxies pull on each other through gravity, and it seemed reasonable that their combined attraction would act like a kind of cosmic brake. There were several possible outcomes imagined for the distant future. If gravity were strong enough, the expansion might eventually stop and reverse, causing the universe to collapse inward again in a scenario sometimes called the Big Crunch. If gravity were weaker, expansion might slow but never completely stop, leaving the universe to drift outward forever. In either case, the expansion was expected to decelerate. But in the late 1990s, astronomers studying extremely distant stellar explosions made a discovery that surprised nearly everyone. These explosions, known as type Ia supernovae, occur when certain kinds of stars reach a critical mass and undergo a sudden, brilliant detonation. Because these explosions release a very consistent amount of light, astronomers can use them as standard candles. By comparing how bright the explosion appears from Earth with how bright it should actually be, scientists can estimate the distance to the galaxy in which it occurred. Two independent teams of astronomers used these supernovae to measure the expansion of the universe across vast cosmic distances. Their goal was to determine how much the expansion had slowed over billions of years due to gravity. But when the results came in, they revealed something unexpected. The distant supernovae appeared dimmer than expected. At first, this might sound like a small observational detail, but it carried enormous implications. If the supernovae were dimmer than predicted, it meant they were farther away than scientists had anticipated. And if they were farther away, the expansion of the universe must have been accelerating, not slowing down. In other words, galaxies were moving apart faster now than they had been in the past. Something was pushing space outward. This mysterious influence was given a name that reflected both its significance and its mystery: dark energy. Dark energy does not behave like ordinary matter. It does not gather into galaxies, form stars, or emit light. Instead, it appears to be an intrinsic property of space itself. As space expands, more of this energy seems to appear, causing the expansion to accelerate even further. Today, scientists estimate that dark energy makes up roughly 70% of the total energy content of the universe. Ordinary matter, including stars, planets, gas, and everything we can see, accounts for only about 5%. The remaining portion is dark matter, the invisible substance whose gravitational pull helps shape galaxies and cosmic structure. This means that the vast majority of the universe is composed of components that remain deeply mysterious. Despite its elusive nature, dark energy has profound consequences for the long-term future of the cosmos. Because it drives the accelerated expansion of space, galaxies that are not gravitationally bound to each other will continue drifting farther apart. Over immense spans of time, distant galaxies will move so far away that their light will no longer be able to reach us. From the perspective of observers inside our galaxy, the universe will slowly appear emptier. Billions of years in the future, many of the galaxies we see today may slip beyond the observable horizon of space. The night sky could become darker and quieter, containing only the nearest cosmic neighbors. The discovery of dark energy transformed our understanding of the universe almost overnight. It revealed that the expansion of space is not simply a relic of the Big Bang, but an ongoing process influenced by forces we do not yet fully understand. And this discovery raises an even deeper question. If dark energy continues shaping the expansion of the universe, what will the far future of the cosmos look like? Will the universe expand forever into cold darkness? Could the acceleration grow strong enough to tear galaxies apart? Or might the universe one day reverse course and collapse again? These possibilities lead us into the final chapter of the story of the universe, a chapter that explores the distant fate of everything that exists. The story of the universe does not end with the formation of galaxies, stars, and planets. Even now, billions of years after the first stars ignited, the cosmos continues to evolve. Space keeps expanding. Galaxies continue drifting through the vast cosmic web. Stars are still being born inside quiet clouds of gas, while others reach the ends of their long lifetimes and fade into stellar remnants. Yet when scientists look far into the future, they see that the universe is gradually moving toward a very different era. To understand what lies ahead, we must begin with the force that now dominates the large-scale behavior of the cosmos: dark energy. Earlier, we saw how astronomers discovered that the expansion of the universe is accelerating. Galaxies are not merely drifting apart due to the initial push from the Big Bang. Instead, the fabric of space itself is expanding faster and faster as time passes. Dark energy appears to act like a subtle pressure woven into the vacuum of space, gently pushing galaxies farther apart with every passing billion years. Right now, this expansion is relatively slow compared to the size of cosmic structures. Galaxies within local groups remain gravitationally bound to one another. Our own galaxy, the Milky Way, for example, is gravitationally connected with the neighboring Andromeda galaxy and dozens of smaller satellite galaxies. Over the next few billion years, the Milky Way and Andromeda will likely merge into a single larger galaxy, forming a new stellar system sometimes called Milkomeda by astronomers. Inside such gravitationally bound regions, expansion has little effect. But on larger cosmic scales, the story is different. Galaxy clusters that are not tightly bound will continue moving farther apart as the universe expands. Over extremely long timescales, the distances between clusters will grow so vast that light traveling between them will struggle to keep up with the expanding space between them. Imagine shining a flashlight across an expanding room where the walls slowly move farther apart. If the room expands slowly enough, the beam can still reach the opposite wall. But if the expansion becomes too rapid, the beam might never arrive. In a similar way, galaxies that are sufficiently distant from one another may eventually cross a threshold beyond which their light can no longer reach us. This boundary is called the cosmic horizon. Anything beyond that horizon becomes permanently invisible to observers within our region of space. Not because the galaxies vanish, but because the expanding universe carries them away faster than their light can travel toward us. Over billions and trillions of years, more and more galaxies will cross this horizon. The universe visible from any single location will slowly shrink. Observers in the far future might see only the galaxies within their own local gravitational group, while all others fade beyond reach. The sky will grow darker and quieter. At the same time, stars will continue evolving within galaxies. Stars are born when clouds of gas collapse under gravity, igniting nuclear fusion in their cores. But the supply of star-forming gas is not infinite. Over extremely long periods, galaxies gradually consume the gas that fuels new stars. Each generation of stars locks more matter into long-lived stellar remnants such as white dwarfs, neutron stars, and black holes. Eventually, star formation will slow dramatically as galaxies run out of the cold gas required to create new stellar systems. This transition marks the beginning of a distant future sometimes called the stellar decline. Billions of years from now, the brilliant star-forming regions that exist today will become rarer. New stars will appear less frequently. The universe will still contain enormous numbers of stars, but most of them will be older, cooler, and gradually fading. The longest-lived stars, small red dwarfs, can shine for trillions of years. These tiny stars burn their fuel extremely slowly, allowing them to outlive larger stars by enormous margins of time. For unimaginably long ages, the universe may remain dotted with these dim but persistent points of light. But even they will not shine forever. Eventually, after trillions of years, nearly all stars will exhaust their nuclear fuel. The brilliant era of star-filled galaxies will slowly fade, leaving behind a universe increasingly dominated by stellar remnants. White dwarfs will drift through space as cooling embers of once bright stars. Neutron stars will spin silently in the darkness. Black holes will lurk at the centers of ancient galaxies, slowly absorbing stray matter that wanders too close. The luminous age of the cosmos will be ending, and the universe will begin transitioning into an era defined not by shining stars, but by the quiet remnants they leave behind. As trillions of years pass, the universe slowly enters a quieter phase of its long story. The brilliant age of star formation that once filled galaxies with radiant light begins to fade. Gas clouds that once collapsed into glowing new stars become increasingly rare. Most of the easily available hydrogen within galaxies has already been used. What remains is locked inside existing stars or scattered too thinly to form new ones. The universe does not suddenly go dark. Instead, its light gradually softens. Many stars that exist today will continue shining for enormous spans of time. The smallest and most common stars in the universe are red dwarfs, tiny stellar furnaces that burn their fuel at a slow and steady pace. Unlike large stars that consume their fuel quickly and die in dramatic explosions, red dwarfs are incredibly efficient. Some of them may shine for trillions of years, far longer than the current age of the universe. For unimaginable lengths of time, these faint stars will remain the last steady sources of light across the cosmos. But eventually, even these patient stars must change. As the hydrogen fuel in their cores is gradually consumed, their fusion processes will slow. Over extremely long periods, the star will no longer be able to sustain the delicate balance between gravity pulling inward and fusion pushing outward. When fusion finally stops, the star will quietly transform into a stellar remnant. For stars similar in mass to our Sun, the final stage is known as a white dwarf. A white dwarf is not a burning star. Instead, it is the dense leftover core of a once luminous star. Roughly the size of Earth but containing a mass comparable to the Sun, a white dwarf is an incredibly compact object. Its material is squeezed so tightly that the atoms inside behave in unusual ways governed by quantum physics. At first, a newly formed white dwarf can still glow brightly from the leftover heat of its former life. But it no longer produces energy through fusion. Slowly, steadily, it begins to cool. Over billions and eventually trillions of years, the white dwarf will fade, radiating its stored heat away into the cold of space. In the far future, these objects may cool so completely that they become dark, nearly invisible bodies sometimes called black dwarfs, though the universe is not yet old enough for any to exist today. Larger stars follow a more dramatic path. Stars many times more massive than our Sun often end their lives in enormous explosions known as supernovae. These violent events scatter heavy elements into surrounding space while leaving behind either a neutron star or a black hole. A neutron star is one of the most extreme objects in the universe. Its matter is compressed so densely that a single teaspoon would weigh billions of tons on Earth. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. Over time, their rotation gradually slows, and their radiation weakens until they become quiet stellar relics drifting through the darkness. Black holes represent an even more extreme endpoint. When the most massive stars collapse, gravity can compress their cores so strongly that nothing, not even light, can escape their gravitational pull. These objects do not shine in the traditional sense, but they can influence their surroundings in powerful ways. Gas falling toward a black hole may heat up and glow brilliantly before crossing the event horizon. Over time, many black holes migrate toward the centers of galaxies, merging with others and growing larger. At the hearts of most galaxies today lie supermassive black holes, some containing billions of times the mass of the Sun. As the universe ages, these black holes will slowly become the dominant objects within galaxies. Meanwhile, the ordinary stars that once illuminated the cosmos will gradually disappear. Some will fade into white dwarfs, others into neutron stars, and the most massive into black holes. The bright stellar populations that once filled spiral arms and galactic disks will thin out as fewer and fewer new stars are born. Galaxies themselves will change as well. Without fresh star formation, the vibrant blue glow of young stars will fade. Galaxies will become dominated by older, redder stars that shine more gently. Over immense spans of time, even these stars will die, leaving behind vast populations of stellar remnants drifting through space. By the time the universe reaches an age of trillions of years, the night sky within galaxies may look very different from what we see today. Instead of brilliant star-filled skies, observers might see only scattered dim stars surrounded by darkness. Yet even in this quieter universe, gravity will continue shaping cosmic structures. Stars and remnants will slowly interact with one another, occasionally colliding or being flung out of galaxies entirely through gravitational encounters. Little by little, the cosmos will grow colder, darker, and more silent. But the story of the universe still will not be finished. Because even the most mysterious objects in the cosmos, black holes themselves, may not last forever. And their slow disappearance will lead the universe into an even deeper chapter of its distant future. As the universe continues aging beyond trillions of years, the bright era of ordinary stars gradually fades into memory. Most stars will have already completed their lifetimes, leaving behind dense remnants scattered throughout galaxies. The cosmos will enter a quieter phase dominated not by glowing stars, but by objects left behind after stellar death. White dwarfs, neutron stars, and black holes will drift slowly through the vast spaces of ancient galaxies. Some of these remnants will remain gravitationally bound within galaxies, orbiting quietly through dark stellar graveyards. Others may eventually be flung into intergalactic space through long chains of gravitational interactions. Yet among all these remnants, one class of object will slowly become the most significant: black holes. Over immense spans of time, many smaller black holes will gradually migrate toward the centers of galaxies. When galaxies merge, their central black holes may spiral toward one another, eventually combining in titanic collisions that send ripples through space-time itself. Each merger produces a larger black hole, steadily increasing the mass of the objects hidden within galactic cores. As this process repeats across cosmic time, black holes may grow to extraordinary sizes. Some could contain billions or even trillions of times the mass of the Sun. These enormous objects will quietly dominate the centers of ancient galaxies long after the stars themselves have faded away. Despite their reputation as eternal objects, black holes may not last forever. In the 1970s, physicist Stephen Hawking proposed a surprising idea that reshaped our understanding of black holes. According to quantum physics, even empty space is not completely empty. Tiny fluctuations constantly appear and disappear at extremely small scales. Pairs of particles briefly pop into existence and then annihilate each other almost instantly. Near the edge of a black hole, something unusual can happen. If one particle from such a pair falls into the black hole while the other escapes, the escaping particle can carry energy away from the black hole itself. From the outside, it appears as though the black hole is slowly emitting radiation. This process is known as Hawking radiation. Because energy is being carried away, the black hole gradually loses mass. For stellar-sized black holes, the process is incredibly slow. A black hole with the mass of our Sun would take far longer than the current age of the universe to evaporate. But given enough time, immense stretches measured in trillions upon trillions of years, even the largest black holes may slowly shrink. As they lose mass, their temperature increases and the radiation they emit grows stronger. Eventually, after unimaginable lengths of time, a black hole may release its remaining energy in a final burst of radiation before disappearing completely. This slow evaporation means that even the most extreme objects in the universe are not truly permanent. During the long era dominated by black holes, galaxies themselves will continue evolving. Gravitational encounters between stars and stellar remnants will gradually alter their orbits. Some objects will fall toward central black holes and be consumed. Others will be ejected into deep intergalactic space. Over immense timescales, many galaxies may slowly lose much of their remaining mass as stars and remnants drift away. Meanwhile, the universe itself continues expanding. Dark energy, which drives the accelerated expansion of space, continues pushing galaxies farther apart. Regions of the universe that were once connected through visible light will become increasingly isolated from one another. Entire galaxy clusters may drift beyond each other's observable horizons. The cosmos grows emptier. In this distant future, the night sky inside any remaining galaxy would appear profoundly different from the one we see today. Instead of a brilliant canopy of stars, the sky might contain only a handful of dim remnants scattered across enormous distances. Beyond the boundaries of the local galaxy group, almost nothing would be visible at all. And yet, even during this quiet era of fading light, time continues moving forward. Black holes slowly evaporate. Stellar remnants cool further. Matter becomes more widely dispersed as galaxies gradually lose their structure. Eventually, the universe may approach an even deeper stage of stillness, a time when almost no large structures remain, and the cosmos becomes a thin scattering of particles drifting through an ever-expanding ocean of space. This distant future is often described as the deep freeze of the universe, and it represents one possible final chapter in the long story that began with the birth of time itself. As scientists study the expansion of the universe and the mysterious influence of dark energy, they begin to imagine several possible futures for the cosmos. None of these outcomes will happen anytime soon. They lie unimaginably far ahead in time, long after stars have faded and galaxies have grown quiet. Yet the physics shaping the universe today allows us to explore how the cosmic story might eventually unfold. The most widely accepted possibility is known as the Big Freeze, sometimes called the heat death of the universe. In this scenario, dark energy remains relatively constant as space continues expanding. Galaxies drift farther and farther apart. Over time, the distances between cosmic structures grow so vast that even light struggles to travel between them. Regions of the universe become increasingly isolated, like islands drifting away across an endless ocean. Inside galaxies, stars gradually exhaust their nuclear fuel. New stars form more rarely as the supply of cold gas diminishes. Eventually, the brilliant stellar era fades into darkness, leaving behind white dwarfs, neutron stars, and black holes slowly cooling and drifting through space. Temperatures across the universe continue dropping. Energy spreads more evenly through the ever-expanding cosmos, leaving fewer differences in temperature that could drive physical processes. Without those energy differences, little activity remains. Matter becomes thinly scattered, radiation grows faint, and the universe approaches a state of near-perfect stillness. In the Big Freeze, the universe does not end in violence. Instead, it slowly fades into quiet darkness over incomprehensible stretches of time. Space continues expanding forever, carrying the remaining particles farther apart until the cosmos becomes cold, dim, and nearly empty. But the Big Freeze is not the only theoretical possibility. Another scenario imagines that dark energy might not remain constant. If the strength of dark energy were to increase over time, the expansion of the universe could accelerate even more dramatically. This idea leads to a scenario known as the Big Rip. In the Big Rip model, the accelerated expansion eventually becomes strong enough to overcome not only gravity between galaxies but also the forces that hold smaller structures together. At first, galaxy clusters would be torn apart as space stretches too quickly for gravity to keep them bound. Later, individual galaxies themselves would begin to unravel. Stars that once orbited peacefully within their galaxies could be pulled away as the expanding fabric of space overwhelms gravitational attraction. Planetary systems might eventually be disrupted as the bonds between stars and planets weaken under the relentless stretching of space. As the expansion grows even more extreme, the forces holding matter together could be affected. Atoms themselves might eventually be torn apart if space expands rapidly enough on microscopic scales. In the final moments of the Big Rip scenario, every structure in the universe, from galaxies to atoms, would be pulled apart by the runaway expansion of space. Fortunately, current observations suggest that if dark energy behaves like a constant property of space, the Big Rip is unlikely. But because the true nature of dark energy is still not fully understood, scientists cannot rule it out entirely. There is also a third possibility, one that takes the universe in the opposite direction. In this scenario, the expansion of the universe eventually slows and reverses. If the combined gravitational pull of matter across the cosmos were strong enough, or if dark energy were to weaken or change its behavior, the expansion of space might gradually come to a halt. After reaching its maximum size, the universe could begin collapsing inward. Galaxies would slowly start moving closer together rather than drifting apart. Over immense spans of time, cosmic structures would grow denser as the contraction accelerated. Temperatures across the universe would rise as matter and radiation became increasingly compressed. This hypothetical future is known as the Big Crunch. In the final stages of such a collapse, galaxies might merge into enormous clusters of matter. Stars would collide more frequently as space shrinks. Eventually, the entire universe could collapse into an extremely hot and dense state once again. Some theoretical models even suggest that such a collapse might trigger another expansion, creating a new cosmic cycle. In these cyclic universe ideas, the Big Bang might not represent the absolute beginning of time, but rather the rebirth of a universe that collapsed before ours. Whether such cycles truly occur remains uncertain. At present, the available evidence suggests that the universe is most likely heading toward the slow-fading future of the Big Freeze. Dark energy appears to be accelerating expansion in a steady and consistent way, making a future collapse less likely. Yet, the universe has surprised scientists many times before, and the deeper we explore its laws, the more we realize how much remains unknown. But before we drift too far into distant futures, it is worth returning to the present moment in this vast cosmic story. Because for a brief window of time, the universe is filled with light, stars, and the possibility of wonder. And that moment includes us. And so, after wandering across billions of years of cosmic history, the story of the universe slowly returns to the present moment. We began our journey at the edge of time itself, in a place where the universe was smaller than imagination and hotter than any star. In those earliest moments, space expanded, forces separated, and the first particles formed within a sea of energy. From a tiny imbalance between matter and antimatter came the atoms that would eventually build galaxies, stars, planets, and life. For hundreds of thousands of years, the universe glowed as a dense cosmic fog, until atoms formed and the first ancient light was released. That light still travels through space today as the faint whisper of the cosmic microwave background, carrying with it the memory of a universe only moments old in cosmic terms. Then came the long darkness. During the cosmic dark ages, hydrogen clouds drifted silently through expanding space while gravity slowly gathered matter into the first structures. Eventually, the first stars ignited, ending the long night and filling the universe with new light. Those early stars lived brief and brilliant lives, forging the first heavy elements inside their cores and scattering them across space in powerful explosions. From those ashes, galaxies formed. Over billions of years, galaxies grew, collided, and merged into the vast cosmic web that stretches across the universe today. Within those galaxies, countless stars were born. Around some of those stars, planets formed. On at least one small world orbiting an ordinary star in the spiral arms of a galaxy we call the Milky Way, something extraordinary happened. Matter became aware. Atoms assembled into molecules. Molecules formed living cells. Life slowly evolved until eventually there were beings capable of looking up at the night sky and asking questions about the universe that created them. In that sense, the universe did not simply produce stars and galaxies. It produced curiosity. And through that curiosity, the universe gained the ability to reflect upon its own existence. When we study the cosmos, When we wonder about distant galaxies or the first moments after the beginning of time, we are participating in a remarkable loop of understanding. The atoms in our bodies were forged in ancient stars that died long before our sun was born. The oxygen we breathe, the carbon that forms our cells, and the iron in our blood all originated in stellar furnaces scattered across cosmic history. We are, quite literally, part of the universe learning about itself. Yet the story we have explored tonight is only one version of the cosmic narrative as we currently understand it. Science continues to refine its understanding of the universe with each new observation. Telescopes grow more powerful. Experiments probe deeper into the laws of nature. And each discovery reveals both answers and new questions waiting patiently beyond the horizon of knowledge. Perhaps future generations will uncover deeper insights into dark energy. Perhaps new physics will reveal what truly happened before the earliest moments we can currently describe. Or perhaps we will learn that our universe is only one small region within a much larger cosmic landscape. For now, though, we exist during a remarkable chapter of the universe's story. Stars still shine across the sky. Galaxies are still visible in every direction we look. The cosmos remains filled with light, motion, and mystery. It is a brief but beautiful moment in a story that stretches across unimaginable time. And somewhere tonight, as the universe continues expanding quietly in every direction, ancient photons from the dawn of time are still passing silently through space. Some of them may even be passing through the room around you right now, carrying messages from a universe that was only a few 100,000 years old. If you are still awake, perhaps your thoughts are drifting gently through these cosmic images, imagining galaxies turning slowly in the darkness. Or perhaps you have already begun drifting into sleep, carried along by the quiet rhythm of the universe itself. Either way, the story continues. Stars are still forming in distant clouds of gas. Galaxies are still moving through the cosmic web. And space itself is still expanding, slowly carrying everything forward into the unknown future. The universe is still unfolding. And tonight, for a brief moment, you were part of its story.